This lab activity is the first serious installment in our last unit of BIO202. We're going to be focusing on the supra-individual levels from that hierarchy of biological organization that we discussed in lecture on the first day of the semester. Remember that? In this unit, we'll be talking about population level biology first, and then community level biology as the last bit of content for our class. In today's lab, we take a close look at age-specific survival as an example of a character or a descriptor that applies to a population of organisms in the same way that a phenotypic character applies to an individual organism. You can measure the length of a squirrel's forearm as a descriptor of that individual squirrel. But what about the animal's likelihood of surviving through its first year of life? In the case of your squirrel, it either survives or it doesn't. If you want to assess squirrel first-year survival rate, you need to have data from a whole cohort of squirrels starting out as newborns. If after 1 year you find that 40% survive and 60% die, you can estimate the first-year survival rate as 40%, right? So let's see what happens if we actually have 40% survival in the first year, and we'll add the assumption that this survival likelihood of 40% per year remains constant for the entire life of the squirrel. We can calculate the number surviving at any given time by taking the number of live squirrels we had 1 year prior and multiplying that by 40%. Let's say we start with 1,000 squirrel newborns. N sub 0 is the number of survivors to age 0, and everybody in our sample survives to age 0. Now come back in 1 year, and how many do we expect for N sub 1? Well, 1,000 times 40%. So N1 is 400. Come back in another year, and we should have 40% times 400. So N sub 2 is 160. Continuing along and filling out this table now, the number of survivors to age 3 is 64. And after 4 years, the number remaining should be 25.6. Decimals are okay here because these are just projections. You don't want to round because that would throw off the estimates for subsequent years. We should have 10.24 5-year survivors and 4.096 6-year survivors. At this point, 4 survivors compared with the starting 1,000 is vanishingly small. And also, the error associated with multiple projections makes it kind of pointless for us to continue. The error for each year's projection to the next would compound the error from the previous year's estimate. Effectively, there would be so much error at this point, 4 survivors might as well be none, or 20. In either case, we still have enough data to draw a curve of survivors over time to depict what constant survival rate of 0.4 looks like. This is the simplest scenario. The survival rate is constant. Here, the annual survival rate is 40%, but any survival rate higher than 0 and lower than 100 will give you the same shape, a more rapid decline initially in flattening out and approaching 0 asymptotically. This is exponential decline, and there are 2 ways of representing this mathematically. You can either say that n sub t plus 1, the number of survivors at time t plus 1, is equal to n sub t times the survival rate, which in our example is 0.4, but to allow for any survival rate, we use the symbol lambda, where lambda is a value between 0 and 1. If you're able to establish an actual set value for the number of survivors at any particular time, here we're given that the survivors to age 0 is 1,000. N sub 0, or N naught, is equal to 1,000. You can project the population size at any time by N sub t is equal to N naught times lambda raised to the tth power. Now both of these equations describe exponential decline. This, by the way, is the same function you'll use in chemistry to describe the declining amount of a radioactive isotope in a sample over time due to radioactive decay. One truth about exponential decline is that the half-life, which is the time it takes for the amount of the isotope to decrease by 1/2, remains constant. In this graph, The half-life for our squirrel cohort is about 0.8 years, because that's how long it took to reach 500 starting from 1000. In another zero point 0.8 years, or 1.6 years from time zero, we've decreased by half again to reach 250 squirrels. Now, I'm doing this graph with you only because it depicts what we're representing in terms that make sense to us. We can visualize 162-year-old squirrels, but we hardly ever use raw number plots like this. Instead, we apply a simple log transformation to the values on the y-axis in order to make age-specific survival graphs much easier to interpret. Let me show you why. Any base logarithm would work here, but we'll go with a natural log, base e, because that's what we'll be using in our population biology lectures later. So now I'll convert all of my number of survivors data into log number of survivors. Note that the number of survivors to age 0 is the number of individuals that we start with, all 1,000. Everybody survives to age 0 in order to be in our sample. Now plotting the log number of survivors on age, the graph is a straight line. This makes sense from a mathematical angle, because if you take the natural log of both sides of our function n equal to n naught times lambda raised to the tth power, you get the natural log of survivors to time t equal to the natural log of n naught plus the natural log of lambda raised to the tth power. And you know that the second term here simplifies to t times the natural log of lambda. So expressing the natural log of the number of survivors as a function of t, you have the natural log of n sub t is equal to the natural log of n naught plus the natural log of lambda times t. The slope of this log transformed graph is the natural log of lambda, and the intercept is the natural log of n naught. In our data set, the natural log of 1000 is 6.908, and that is our y-intercept. This linear plot is also convenient because it sets the baseline for the two main kinds of deviation from constant survival that we frequently find in nature. Deviations that we expect because we know that constant survival isn't realistic, right? Now, when, over the normal range of lifespan for any given species, would you expect survival rate to be lower, and when might survival be predictably higher? Think about that for a minute. Well, usually the weakest individuals in a population, those that are most vulnerable to the many potential causes of death experienced by organisms, such as starvation, predation, disease, are the youngest and the oldest. And so, for example, if the survival rate for young adults peaks somewhere higher than 40%, maybe at 70%, the rate of decline is a little flatter in the middle years, but steeper at the beginning. This is due to the higher juvenile mortality, and steeper on the right because old organisms are subject to the ravages of age and are thus more susceptible to the many potential causes of death. In biology, we refer to this increasing mortality as one advances in age as senescence, a word that is etymologically related to senior and senile. For a great number of species, only one of these two phenomena, juvenile mortality or senescence, will dominate the age-specific survival pattern. Take oysters, for example. Each female oyster will produce 50 million to 60 million eggs each summer. From a single oyster population, there will literally be billions and billions of newborn oysters, and the survival rate is just really dismal for that first year of life. A one-year-old oyster might be just a little button of a thing and still subject to pretty high mortality, but it has a much higher expected survival rate compared with a newborn. Survival gets even better in the third year, and as the oyster gets larger, the survival rate either remains the same or gets incrementally better. You don't have old, weak oysters needing to go to oyster-assisted living centers. As oysters grow older, they get better at surviving, but there just aren't too many of them because their survival rate is so low at the start of their lives, and sooner or later they'll cross paths with the hungry starfish. Now, there may be a really big 100-year-old oyster out there somewhere, but if it exists, it's so rare that you can hardly expect it to drive oyster life history evolution. The vast majority of living oysters will be in the 0 to 10-year age range. Now, if you plotted age-specific survival for oysters, the slope would start off incredibly steep on the left, and then it would become less steep as the oysters get bigger and better at surviving. In the log transformed plot, this results in a concave up curve because the survival rate is not constant. It starts off low and improves over time. Senescence is not a significant factor for oysters, but juvenile mortality certainly is, and this concave up shape of the age-specific survival curve results, and we call this a type 3 age-specific survivorship curve. Other species might have a relatively high survival rate early in life. Maybe juvenile mortality is there, but not very severe. Then, with a large proportion of individuals actually living to advanced age classes, there's a greater opportunity for senescence to have an effect. The human population is a great example of this. It is statistically true that a 20-year-old has a lower likelihood of dying at any moment as compared with a 50-year-old. The 50-year-old's likelihood of dying is lower than that of a 60-year-old, and the 60-year-old is less likely to die as compared with an 80-year-old. Once you get to a certain point in life, the older you get, the greater your likelihood of dying, or in other words, your survival rate is tanking, just getting incrementally worse with every passing day. At what age do humans reach their peak survival rate? It's about at age 10, give or take a year. Sorry, but all of you are on the downhill slope already, though some of us are further ahead than others. So the curve would look something like this. High-ish mortality rates until age 10, where the curve reaches its shallowest slope. And from then on, survival rates just get lower and lower, so the curve bends downwards, creating a convex subsurface. This is your type 1 age-specific survivorship. Type 2 age-specific survival is constant survival, constant mortality. This is the one that we started off with. There are actually a few examples you can dig up where populations show something that approximates constant survival. Seagulls, and oddly enough, squirrels, seem to conform pretty closely to a type 2 curve. The situation setting this up would have to include a relatively high early survival. Both squirrels and seagulls have large babies that are pretty good at surviving, coupled with a pretty substantial mortality rate thereafter. Perhaps if survival were generally higher and we had actually a larger number of geriatric gulls or squirrels, then we might see some effects of senescence. Today's lab activity involves simulating populations and generating age-specific survival curves for 3 kinds of organisms. We'll cover the actual activity in the next video.